High-frequency noise at a performing arts building can stem from several sources. Airport radar emits high-frequency radiation capable of interfering with electronic equipment. Light rail overhead catenary lines are another potential source of high-frequency noise. The building's large metal roof and exposed steel can act as antennas, picking up electromagnetic interference from the surrounding environment. While all connections and bonding may have been checked, sources of noise could still exist within the building. To address this, consider several troubleshooting steps and mitigation strategies. Firstly, adding shielding or filtering to the equipment can reduce noise susceptibility. This includes using ferrite cores, shielded cables, or electromagnetic interference gaskets. Secondly, double-check all grounding and bonding connections to ensure proper electrical and electromagnetic isolation. Thirdly, an RFI scanner can identify noise sources and their frequency range, helping to narrow down potential culprits. Contacting the airport and light rail authorities to inquire about known high-frequency noise emissions in the area is another avenue. They may have mitigation measures or information to assist in troubleshooting. A thorough inspection of all equipment in the building should be performed, looking for any signs of malfunction or improper connections that could contribute to the noise. Shielding and absorption techniques can also be implemented. Installing electromagnetic shielding materials around sensitive equipment and absorbing excess noise using acoustic foam or other sound-absorbing materials can be effective. Implementing filters tuned to specific frequencies, such as those of airport radar or light rail noise, can block out unwanted interference. Physically isolating sensitive equipment from potential noise sources, such as using vibration isolators or placing equipment in separate rooms, is another strategy. Work with the airport and light rail authorities to explore mitigation measures or changes to their operations that could reduce noise interference. The measured noise of 45 to 88 kHz at 34 to 185 mV between an isolated equipment ground, and neutral suggests a common mode noise problem. Because it is consistent throughout the building, it points to an external source affecting the entire electrical system or a systemic grounding issue within the building. Given the building's proximity to an airport and light rail, these are prime suspects for introducing high-frequency noise. A large metal roof and exposed steel structures can act as unintentional receiving antennas, exacerbating the problem. Here's a detailed breakdown of potential sources and mitigation strategies. Firstly, airport radar systems can emit pulse radio frequency signals that operate in the gigahertz range, but harmonics and lower frequency components can extend into the kilohertz range. If the building is directly in the path of the radar beam, the received signal strength could be significant. Secondly, light rail systems that use overhead catenary lines often employ high voltage alternating current power. The switching and rectification processes in the trains and substations can generate high-frequency noise that propagates through the catenary lines and radiates into the surrounding environment. The proximity of the building to the tracks, less than 50 feet, increases the likelihood of interference. Thirdly, internal sources, despite initial checks, could be contributing to the problem. These can include switching power supplies, variable frequency drives, lighting systems, and other electronic equipment that generate harmonics and high-frequency noise. Improper grounding, loose connections, or inadequate shielding within the building's electrical system can amplify these internal noise sources. Metal structures within the building, including the roof, walls, and conduit, can act as resonant cavities, amplifying specific frequencies of noise. To systematically troubleshoot and mitigate this issue, follow these steps. Firstly, perform a detailed grounding and bonding inspection. Verify that all grounding conductors are properly sized and connected according to the National Electrical Code, specifically Articles 250.4, 250.24, and 250.166. Check the impedance of the grounding electrode system to ensure it meets the requirements of NEC 250.53. Measure the voltage between the isolated ground, equipment ground, and neutral at various points in the building to identify any potential ground loops or voltage differentials. Secondly, use a spectrum analyzer to identify the specific frequencies and amplitudes of the noise signals. This will help determine if the noise is originating from the airport radar, light rail system, or internal equipment. Record the measurements at different times of day to see if there are any patterns or correlations with the operation of the airport or light rail. Thirdly, install a power line filter at the main electrical service entrance to block high-frequency noise from entering the building's electrical system. Choose a filter that is specifically designed for high-frequency noise suppression and has a cutoff frequency below the lowest frequency of the noise signals you are trying to eliminate. The filter should be properly grounded to ensure effective noise reduction. Fourthly, apply shielding techniques to sensitive equipment and cables. Use shielded cables for all signal and power connections to prevent noise from being conducted into the equipment. Enclose sensitive equipment in metal enclosures to block electromagnetic radiation. Apply conductive gaskets to the seams of the enclosures to ensure a tight seal. Fifthly, install ferrite beads or chokes on cables to suppress high-frequency noise. Wrap cables around ferrite cores to increase their impedance at high frequencies, which will attenuate noise signals. Place ferrite beads close to the equipment to minimize the length of unshielded cable. Sixthly, implement proper grounding techniques for sensitive equipment. Connect equipment to a dedicated ground point to minimize ground loops and voltage differentials. Use star grounding configurations to prevent noise from propagating through the grounding system. Ensure that all ground connections are clean and tight to provide a low impedance path to ground. Seventhly, isolate sensitive equipment from vibration and mechanical noise. Use vibration isolators to decouple equipment from vibrating surfaces. Install acoustic panels to absorb sound waves and reduce noise levels in the equipment room. Eighthly, coordinate with the airport and light rail authorities to discuss potential noise mitigation measures. Share your findings and measurements with them to help them understand the impact of their operations on your building. Explore the possibility of implementing noise reduction technologies at the source, such as improved filtering on the light rail catenary lines or directional antennas for the airport radar. Ninthly, inspect the building's electrical system for potential sources of internal noise. Check all switching power supplies, variable frequency drives, and lighting systems for proper operation and shielding. Ensure that all equipment is properly grounded and bonded. Replace any faulty or noisy equipment with more efficient and quieter models. Tenthly, consider installing a dedicated isolated ground system for sensitive equipment. An isolated ground system provides a separate grounding path for sensitive equipment, preventing noise from the building's main grounding system from interfering with the equipment. The isolated ground system should be installed according to NEC 250.146 and should be carefully designed to avoid creating ground loops. To further refine the troubleshooting process, consider these more specific steps. Firstly, to determine the source of the noise, use a portable radio frequency interference or RFI detector. These devices can pinpoint the direction and strength of radio frequency signals. Walk around the building's perimeter and interior, noting the areas where the signal is strongest. This can help identify whether the noise is coming from outside, like the airport or light rail, or from within the building itself. Secondly, if you suspect the airport radar is the source, try to correlate the noise with the radar's operation schedule. Contact the airport authority to inquire about the radar's operating frequency, pulse rate, and power output. Compare this information with the frequencies you are measuring in the building. It may be possible to determine if the radar signal is directly coupling into the building's electrical system. Thirdly, regarding the light rail, investigate the grounding practices of the catenary system and the trains themselves. Stray currents in the ground can induce noise in nearby electrical systems. The Light Rail Authority may be able to provide information on their grounding practices and any known noise issues. Fourthly, within the building, pay close attention to lighting systems, especially if they include electronic ballast or dimming systems. These can be significant sources of high-frequency noise. Try turning off different lighting circuits to see if the noise levels decrease. Fifthly, variable frequency drives, or VFDs, used for motors can also generate substantial noise. Ensure that all VFD are properly shielded and grounded. Use line reactors or filters to reduce the noise generated by the VFD. Sixthly, switching mode power supplies, commonly found in computers, audio equipment, and other electronic devices, are notorious for generating high-frequency noise. Use power conditioners or filters to clean out the power supply to sensitive equipment. Seventhly, cable runs can act as antennas, picking up noise from the surrounding environment. Separate power cables from signal cables to minimize the coupling of noise. Use shielded cables for all critical signal paths. Eighthly, grounding is crucial. Ensure that the building's grounding system is properly designed and installed. All metallic components, including conduit, cable trays, and equipment enclosures, should be bonded together to create a low-impedance ground path. Use a ground impedance tester to verify the effectiveness of the grounding system. Ninthly, consider using a Faraday cage for particularly sensitive equipment. A Faraday cage is an enclosure made of conductive material that blocks electromagnetic radiation. This can be an effective way to isolate equipment from external noise sources. Tenthly, if the noise is particularly problematic, it may be necessary to hire a qualified electromagnetic compatibility or EMC consultant. An ENC consultant can perform a thorough site survey, identify the sources of the noise, and recommend appropriate mitigation measures. The consultant can also help with the design of shielding and filtering systems. In addition to these steps, remember that high-frequency noise can also affect the performance of audio equipment by causing audible hum, buzz, or distortion. This is because the noise can be demodulated by nonlinear components in the audio amplifiers and mixers, resulting in unwanted audio signals. To minimize the impact of noise on audio equipment, follow these recommendations. Firstly, use balanced audio connections whenever possible. Balanced connections are less susceptible to noise pickup because they use differential signaling, which cancels out common mode noise. Secondly, avoid ground loops in the audio system. Ground loops occur when there are multiple ground paths between pieces of equipment, creating a loop that can carry noise currents. Use a single-point grounding system to minimize ground loops. Thirdly, use isolation transformers to break ground loops between equipment. Isolation transformers provide electrical isolation between the primary and secondary windings, preventing noise currents from flowing between the equipment. Fourthly, use power conditioners or filters to clean up the power supply to the audio equipment. Power conditioners can remove noise and voltage fluctuations from the power line, improving the performance of the audio equipment. Fifthly, shield audio cables and equipment to prevent noise pickup. Use shielded cables for all audio connections. Enclose audio equipment in metal enclosures to block electromagnetic radiation. Sixthly, locate audio equipment away from noise sources. Keep audio equipment away from power transformers, lighting dimmers, and other sources of high-frequency noise. Seventhly, use proper gain staging to minimize noise in the audio system. Set the gain of each stage of the audio system to optimize the signal-to-noise ratio. Eighthly, test the audio system for noise with a signal generator and oscilloscope. Inject a test signal into the audio system and observe the output on an oscilloscope. Look for any signs of noise or distortion in the output signal.